simulations. And this is sort of a world fastest class because it is operated K and Fugaku. And also we do the coupled simulation with traffic demand and traffic flows. Next one, please. And also we do economic simulations. And to somehow validate and give initial conditions, we utilize urban area data. So next one, please. And this is not the easy stuff. This is actually the visions of an agent. So bottom side, each agent see 360 degrees sort of scanning, and this agent decide which way to go. That's why we can make a very sophisticated simulations of intersections at the road. So we can do sort of coupled simulation of the pedestrians and the vehicles. So next, please. And this is a dynamic road balance of this agent simulations. As you know, that agent moved to one path, so road balance is easily broken. That's why we made a very sophisticated road balancings. Next, please. And then we apply this social simulation for the traffic demand and flow. There are many traffic flow simulations, but it's very important to consider traffic demand post the earthquake. So we do this traffic demand simulations. Next, please. This is a coupling of demand and flow simulation. Just keep hitting, please. So it's sort of flow of these simulations. Okay, so the final one is a BELLMAN'S equation. I believe that this is very new to most of the participants. This is a standard formulations of economic simulations. And we have to solve this bit difficult set of equations in using supercomputers. So next, please. And this is agent simulations. This is not the simple stuff again, and we have to consider banks or central banks or government, and we have to consider many links between these agents of a huge scale to a small household. So next, please. And this is social simulations. We are now calling this simulation one-to-one scale model of Japanese economies. We have done it the EU, one-to-one scale modeling. We succeeded. So 100 millions or the billions of agent or economic agent can work coupling together. So next, please. And this is an integration of social sciences and simulations, the traffic simulations, economic simulations. These two simulations will be operated once the science simulations and engineering simulations are completed. These two simulations provide initial conditions, and the traffic simulations and economic simulations will be started. So next, please. And we have to make automated model constructions for like bridges. And we do some automated construction, model construction technique. So next, please. Whoa. And structural damage and road networks, we have to do these things. The left top is a structural seismic response, and the right is a road network. And we combine them, we consider the availability of a road network, and we consider the traffic flow after we analyze the traffic demand. So please hit the return. Yeah. And this is sort of availability of a road we can simulate and run these traffic simulations. So next, please. Oh, next, yes. So similarly, we do the economic simulation as well. Please hit return. Okay. And now I have 5 minutes. So we apply this one to the 2 big earthquakes which expect to hit Japan. The first one is the Tokyo metropolis earthquake. we targeted all Tokyo areas, and we mainly concerned about traffic simulations after the structural damages. So next, please. So this is a building damage considering uncertainty over surface layers. And we have, for one given scenarios, we consider the difference in the surface layers properties and consider building damages. So red is a severe damage, and the blue is a non-damage. And depending, of course, on uncertainty of surface layers, we can tell the expected building damage distributions. Next, please. Considering this one, we calculate remaining load widths to determine the load capacities. So next, please. Then considering the traffic demand, we calculate the traffic density. And depending on the scenario of case 1 and case 2, we can see the damage and the traffic densities. And for this Tokyo metropolis earthquake, it turned out the traffic density is not as high as expected. So next, please. Also, degree of we can calculate the degree of congestions, and let me repeat. In these simulations, this degree of distribution of the degree of congestions are not that bad as expected. As expected mean using an ordinary conventional method of estimating the traffic damage or these things. Okay, next, please. So next one is the Nankai Trough earthquake. Compared to the Tokyo metropolis, the target area is larger, and residential number of residential buildings and the road network is increased. That's why we need supercomputers. So next, please. So this is automated model constructions. We made a road and the bridge and the structures using the available data of limited quality and quantity. We somehow make models and calculate these things. So next, please. So this is a building models. We have a wood structure, steel, reinforced concrete, and the steel reinforced concrete. And the two-story to the high rise, we model it. Next, please. We also made a ground models. Unfortunately, the supercomputer cannot calculate all the regions. So expect for the major part of the Osaka area, we do conventional analysis anyway to get the ground computations. So next, please. And I hope this works. So this is the track flow simulations. Would you please hit the return? For this Kansai area, we calculate ordinary traffic flow to somehow validate or examine the quality of our traffic flow simulations. So it's in the range of acceptable for the traffic transportation engineer. So next one, please. So the post-earthquake, due to the damage of structures in the road network, we have a very bad, say, traffic flows. Unlike a Tokyo case, the in the Nankai earthquake, the traffic situations in this area is worse than expected. So next, please. So this is a result. Depending on the ordinary case, the earthquake scenario is east-oriented, or if we consider the larger amplitude, the traffic flow congestion state is very different. But the simulation tells the expected traffic flow is worse than expected. This is quite a difference in the Tokyo case. So next, please. And we do the economic simulations concerning all the Tokyo cases, solving this BELLMAN'S equations. So next, please. And this is economic recovery. This is a time series expectations, and each industry-wise, we calculate the recovery of economic activities. Next, please. And the important thing that, that we somehow measure the effect of recovery plans. And we consider the 4 plans, which is shown in the above. And we do check the effect of a recovery plan. And I have to tell you, this simulation is very, very bad. This is because that if we speed up 9 months, still economy recovery doesn't change very much. And only the first few weeks, this economy recovery plans make a difference in economic activities. I believe this is far from the reality. So all the effort actually goes in vain. But I have to emphasize, we somehow integrated these earth science simulations and engineering simulation to the social science simulations. And I want to say that there are many rooms to be improved for the social science simulations, but we surely need these things to consider the more effective recovery plan or retrofitting plans. So next, please. So this is my concluding works. Anyway, using supercomputers, and which some of them will be transported to the Fugaku project. In Japan, we are making integrated earthquake simulations, which combine social earth science simulations, earthquake engineering simulations, and the social science simulations. So this is the end of my talk.
Thank you.